Welcome to the NPTEL online certification course on deep learning. You remember in the previous class we have started our discussion on optimization techniques and we have talked about the different optimization techniques like stochastic gradient descent. We have talked about batch optimization and we have also talked about mini batch optimization. In today's lecture, we are going to talk about optimization in machine learning, in particular that how optimization in machine learning applications differs from general optimization problems. We will also talk about linear and logistic regression, Softmax Classifier, and we will also talk about the nonlinearity, how nonlinearity is important in case of deep learning or machine learning applications. So, let us first talk about how machine learning optimization in machine learning is different from general optimization techniques. So, what you do in case of optimization? The goal of optimization is to reduce a cost function given by say J W, where W is the parameters which defines your machine learning algorithm. So, you optimize this cost function J W or minimize the cost function J W in order to optimize some performance measure of your learning algorithm or machine learning model. So, what is the performance measure in case of machine learning that we have discussed so far? The problems that we have considered are mainly categorization or classification problems. That is, given objects or signals belonging to different categories, we try to identify that which signal or which object belongs to which kind of category. So, if your categorization or classification is correct, there is no error. If the classification is incorrect, you incur some error. So, the performance measure with respect to machine learning is how accurate your classification or categorization decision is. And in order to do that, you minimize a cost function J W, which is this cost function J W is comprises of the loss that you incur during classification of the training data. Now, if you talk about the pure optimization problem, in case of pure optimization problem, the optimization criteria or the cost function J is minimized and that is the goal in and of itself. In other sense, suppose you are given a set of observations in 2 dimension, that is I may have x y pairs where I assume that x is an independent variable and y is a dependent variable. And if there is sufficient reason to believe that the relation between x and y is linear, then given a set of observations, what we would like to do is we would like to fit a minimum error state line passing through the set of observed data, and that is the aim. And when you try to find out this state line which minimizes the error, actually you go for minimization of sum of squared error, and once the line is fit, your goal is satisfied. But when you talk about machine learning, in case of machine learning, we minimize the loss function or cost function J W, where W is the parameters of your machine learning algorithm or the machine learning model. But this minimization is done on the training data or the training samples, or in other words, what you try to minimize is the training error. But what is our actual aim? Our actual aim is not to classify the training data, because for the training data the classes are already known. So, what is the great thing about classifying the data which are known already? So, our aim is not to correctly classify the training data, but our aim is that the machine that you have trained using the training data or the labeled data, that same algorithm or the machine has to be used for classification of unknown or unforeseen data, which the machine has not seen before. And for this unknown data, the class belongingness is not really known, because if it is known, then I do not have to classify. So, for this, what my aim is that though I am training the machine or minimizing the error on the training data, but my aim is that the same machine has to perform well on the actual data or the test data. So, I want that not only the training error to be minimized, but also the test error is to be minimized. So, how do you know the test error? Because as I said that for your real life classification problem, that class belongingness of the data is not known. So, what you do is you set aside a set of level data which are known as test data, for which the classes are known, but you do not use that set of data or test set for training the machine. So, in that case, I can compute what is the error given by the machine while testing, but while training you use one set of data which is training set, for testing you set another set of data which is test set. But again, when you come to actual application, when you want to deploy this machine learning model, machine learning algorithm for classification or recognition, there the class belongingness of the data is not really known. So, accordingly, you incorporate some test error when you are testing the machine on the test set of data which are not actually used for training purpose. And while doing so, you incorporate some error or some loss which are the test, which is known as the test error or generalization error. So, in case of machine learning algorithms or optimization in case of machine learning, though I am optimizing the machine on the training data, but my aim is that the same machine should perform well on the test data as well as on the real life data. So, that is the basic difference between a machine learning algorithm or optimization in case of machine learning algorithm. So, naturally, because the test data has not been used for training the machine, how do we really know or how do we really guarantee that the machine or algorithm which has been trained on the training data will also perform well or give lesser test error while testing on the test data, or it will also give minimum error when you actually deploy the machine for real life classification problem. So, truly speaking, this cannot be guaranteed, but under certain assumptions we can say with certain degree of confidence that the machine will also perform well on the test data. And for that we make some assumptions popularly known as IID assumptions. So, what we assume is that both the training data and the test data, they are generated by a probability distribution, which is known as the data generation process or data generation model. We also assume that the data samples in each set in data set are independent. That is, one sample or one vector is independent of the other vector. And we also assume that the training set and test set are identically distributed. So, when we talk about the data distribution, the distribution of the training set of data and the distribution of the test set of data, they are identical, and that is what is known as IID assumption, that is independent identically distributed set of data. Normally, the performance of a machine learning algorithm is measured by its ability to perform two tasks. One of the tasks is that it has to make the training error small, that is, while training the machine on the training set of data, the training error that you incorporate, that should be small, and only when it is very small, ideally it should be 0, we assume that the machine or your algorithm is properly trained or it has learned the classes. And secondly, when you test it, so while testing on the test data, and as we said before that the test data is not used during training the machine, though we know what are the class belongingness of the test data. So, once the machine is trained on the training data, you use the same machine on the test data. And in case of test data, ideally we want that the error should be minimum or the error should be 0 in ideal cases, but practically that may not be possible. So, while applying the same machine on the test data, we get some test error. So, again the performance of the machine learning algorithm is measured in terms of what is the gap between the training error and the test error. So, we always expect that whatever is the training error, the test error should also be similar. That means the gap between the training error and the test error should be as small as possible. So, these are certain assumptions, and under those assumptions we talk about how the machine learning algorithm actually perform. Now, these assumptions and the performance measures that lead to two very important problems, two challenging problems. One of them is known as underfitting problem, and the other one is known as overfitting problem. So, what is underfitting problem? Underfitting problem is when your model or the machine is not able to obtain sufficiently low training error. That means, it is not performing well on the training data itself. So, the training error is not acceptably low, and as we said that in ideal cases we expect this training error should be 0. That means, all the training samples which are given for training the machine, they should be correctly classified, and then only we get the training error to be 0. And the overfitting says that the gap between training and test error is too large. So, there may be cases that while training we have been able to design a machine or a model where the training error is minimum, but the same machine when it is applied on the test data is quite large. That means, there is a gap between the training error and the test error. So, overfitting says that your model has been able to capture even the minute differences in the test data, and while doing so, the model is so tuned to the test data that it has lost the generalization, and it is not being able to perform well on the test data, and that is what is known as overfitting problem. So, these problems of overfitting or underfitting can be controlled by altering another property of the model, which is known as model capacity or capacity of the machine learning algorithm. And this capacity is nothing but a set of functions the learning algorithm can select as being the solution. So, we will just see after this, and you remember that all the problems that we have considered, we have discussed till now, they are linear problems. We have assumed that given data belonging to two different classes in the feature space, I can have a hyperplane in the feature space. I can define a hyperplane in the feature space where all the training data belonging to one class falls on positive side of the hyperplane, and all the training data belonging to other class falls on the negative side of the hyperplane. That means, the data set is linearly separable. But what happens if the data set is not linearly separable? I may not be able to pass a plane or a hyperplane passing to the data sets belonging to two different classes. That means, in that case our linear assumption is not correct, is not sufficient. Instead of a hyperplane, if I pass a curve or a surface, a curved surface, then a curved surface may be able to separate those two set of data belonging to two different classes. So, that is what is known as the set of functions. Always the linear function may not be sufficient. I may have to go for functions of higher order, maybe quadratic, maybe cubic, or even fourth order, fifth order, and so on, which is known as the capacity. So, if I control the capacity or the set of functions the training algorithm can adopt as required, then possibly we can have a control over the overfitting and underfitting problems. And there also, it is not that that simple or that easy, because it is quite possible that say for example, a data set which is sampled from a quadratic function, If I want to fit a quadratic function, it will be properly fit. That means all the data will be properly fit to the quadratic curve. If I try to fit a linear surface, then obviously I will incorporate some error. If I want to fit a data of say higher dimension, say of a curve of higher dimension, say order 5 or order 7 and so on, then it is possible that for the given set of data, I will have no loss, there will be no error, but the data is too specific for that set of training samples. It is not general enough to perform well on unknown data set or test data set. So, even selecting the capacity of the model or capacity of the of the machine learning algorithm is also a difficult task or a challenging task. So, here we have talked about that what is the difference between a general optimization task and an optimization task as applicable to machine learning algorithms. Because in case of machine learning algorithms, though we are optimizing on the training set of data, but actually I want to perform on a different set of data, which is test set of data. Right. So, now I talk about two problems which are known as linear regression and logistic regression, and we will see the importance of this. So, what is linear regression? You find that so far all the problems or the examples that we have considered as we have just mentioned now, that I have considered only the linear problems. That is, given two sets of data, I should be able to find out a straight line in 2 dimension or a surface or a plane in 3 dimension or a hyperplane in even higher dimension. So, effectively there what I want to do is this model that maps a feature vector of dimension d to a scalar y which is a linear number. So, this is actually put in this form that this is a mapping which maps a feature vector x of dimension d. So, we write it this way that x belongs to R d. So, it maps this feature vector x to an y, or in the other words that given feature vector x, we want to predict what is y, what is the value of y. So, I can write this in the form of a linear equation of this form, that y hat is equal to w transpose x, where w is the weight vector. And based on the value, so while training what we try to do is, we try to minimize the error between actual y, which is the true class that is given for the set of data, and this y hat that is predicted. We want to minimize this error during the training operation. And during classification what we do is, based on this predicted value of y, which is y hat, we take a decision that whether we should classify x to class 1 or we should classify x to class 2. So, for a binary classification problem that we have done previously, we have discussed previously, we have seen that if y hat is positive, that means if it is greater than 0, then we classify x to class 1, and if y hat is negative, that it is less than 0, then we classify x belong to class 2. Now, what is this linear regression actually? If you look at this expression, that is w transpose x, given this example, here we have taken the same example in your previous discussion, that we assume that this is the set of data, the set of feature vectors which belong to class say omega 1, and this is another set of feature vectors that belong to class omega 2. So, for every point, and this is my hyperplane given by the equation w transpose x equal to 0. So, you find that for every point belonging to omega 1, your w transpose x will be greater than 0. For every sample belonging to class omega 2, w transpose x will be less than 0. And in fact, this w transpose x upon mod of w, that actually gives you an idea of what is the distance or perpendicular distance of the vector x from the plane w transpose x equal to 0. So, that measure gives us a confidence of how accurate your classification is, because given these two sides, if I have a vector over here which is far away from the separating plane, in such cases obviously I can tell with high degree of confidence that my classification result is correct. Whereas, if I have a data somewhere over here where the distance of this data of this vector from the separating plane is very small, my confidence level is not that high, though here the distance becomes greater than 0 as w transpose x becomes greater than 0. So, I classify this to belong to class omega 1, but my confidence level is not that high as I have confidence in this particular case. So, I have a physical interpretation of the value of w transpose x, that it says that how well inside the class the data is. And if it is very high, w transpose x is very high on the positive side, then with guarantee I can say that yes, this belongs to class omega 1. And if it is very low, that is w transpose x is high magnitude, but it is negative, then I can tell with confidence that yes, it belongs to class omega 2. But if the value is low, my confidence level comes down. So, I can have another interpretation of this measure, that is what is given by logistic regression. So, in case of logistic regression, I can have a probability measure, that is I can compute that what is the probability of y, which is the class index, given a feature vector x and the model parameter w, which is written in this form p y given x and parameter vector w. That can be written as a function of sigma w transpose x. So, again you find that this w transpose x, what you said earlier, is a measure of distance. This was a distance measure, distance of x from the surface w transpose x equal to 0, and using this sigma function I can convert this to a probability measure. So, as we said that if my data vector x is far away from the separating plane, my confidence level is very high. So, that in other sense I can say that the probability of class y is very high. So, I can convert this distance measure into a probability measure, and that is what is done by this function sigma. And I can write this function as a sigmoidal function, which is given like this. So, this sigmoidal function is nothing but sigma w transpose x equal to 1 by 1 plus e to the power minus w transpose x. And if I plot this function, the function will have a plot like this, which is a sigmoidal function. So, if I plot sigma w transpose x versus w transpose x, I get a curve as shown on this side, and here you find that as w transpose x become high, as you increase w transpose x. So, coming to our previous interpretation of distance from the separating plane, as the distance from the separating plane is very high, the probability goes on increasing and asymptotically it goes to 1. On the other hand, if w transpose x is negative, you find over here. So, here you find that if w transpose x is equal to 0, what I get is sigma w transpose x, that is equal to half, right. So, from here e to the power minus w transpose x, if w transpose x is 0, that means e to the power minus w transpose x is 1. So, I get simply the value of half. So, as at w transpose x equal to 0, the value of this sigmoidal function is half. That means, if the feature vector lies on the separating plane, it has equal probability of belonging to class omega 1 and class omega 2, or in other words, I cannot really classify the feature vector x. Whereas, as W transpose x becomes greater than 0, its probability of belongingness to class 1 goes on increasing, and when W transpose x becomes very high, that is the distance from the separating plane is very high, the probability goes towards 1. Coming to the other side, as W transpose x becomes negative and becomes lower and lower, that is, it is more on the negative side, asymptotically your sigma W transpose x becomes tends to be 0. That means, its probability of belongingness to class omega 1 is almost 0. And when I compute the probabilities, because I am considering only two classes omega 1 and omega 2, so I can say that the probability that it belongs to class omega 1 and the probability of it belonging to class omega 2. So, what I can write is, I can write it in this form, that probability y equal to 1 given x and w, that is the probability that x belongs to class omega 1, and I can also write the probability that x belongs to class omega 2. So, probability y is equal to 2 given x and w. So, if I add these two, that should be equal to 1, because I am considering only two classes omega 1 and omega 2. So, here, as the probability belonging to class omega 1 becomes high, the probability of belonging to class omega 2 becomes lower. And this is the point when both of them are equal, that is, probability of belongingness to both the classes are half to omega 1 as well as half to omega 2. So, that is what is logistic regression, that is converting my distance measure or the confidence measure to a probabilistic measure, that what is the probability that x belongs to class omega 1 or what is the probability that x belongs to class omega 2. There is another concept which is known as Softmax Classifier. So, earlier this linear regression or logistic regression which we have discussed, those are with respect to our binary classifier or two class problem. But when we have a multi-class problem, we have discussed earlier that I can have a linear machine, where using a linear machine, the parameters, set of parameters are represented as a weight matrix W, where vectors in every row of the weight matrix W, we have said represents a prototype or represents a class or a sample belonging to a particular class, that is a representative of a particular class. So, if I have say k number of classes, I will have k number of rows in the weight vector. And what that set of or matrix of weight vectors give is, when you multiply that with your given feature vector, you get a score vector. And we have seen that the score vector is a set of real numbers. So, if I have got k number of classes, my score vector x was having k number of elements. So, if I have a feature vector x which belongs to class omega, which belongs to class say y I, the class index is y I, then the corresponding score is given by s of y I, which we have computed as w x I and the y ith component of that, or this also you can write as w y ith row, the vector corresponding to y ith row, take the transpose of that vector and multiply that with x I. So, that gives you the score of class y I for feature vector x or x I, which belongs to class y I. That is, we already know, because this is a training vector. So, again this is on the output of a linear function, as we have done in case of logistic regression. I can also convert this to a probabilistic measure. So, I can say that what is the probability of class y I given sample xi and your parameters w given by the parameter matrix or the weight matrix w. And we can compute this as e to the power sy upon e to the power sj, where the sum of e to the power sj in the denominator, where the summation has to be taken over all j. So, you find that this also converts our score factors or the score values to different classes in a probabilistic measure, that what is the probability of class yi given a feature vector x or given a feature vector xi. So, we will continue our lecture further. Thank you very much.